Hello everyone. In this last lecture about the Thevenin-Norton equivalency, I'm going to discuss a specific or special case of a network, two actually, and with this we're going to conclude our discussions. Okay, let's assume that you're given this circuit and you're tasked to develop a Thevenin or Norton equivalent for that circuit. Our process went something like this. First, for both of the cases, we either calculated the open circuit voltage or the short circuit current. If you calculate the open circuit voltage, that would be equal to your Thevenin voltage. If you calculate your short circuit current, that would be your Norton current. Now, if you notice, if I leave this circuit open and look at this circuit, it's just a network of passive resistors. In other words, there is no independent source of energy within this network. So if I leave this open, there is no reason for any electron to move within this circuit. If just leave this open, there's no energy, source of energy here. And what that means is that the open circuit voltage here would end up being 0. The same way with a short circuit current. So if I leave this as a short circuit, same thing. Since there is no source of energy here, there's no reason for any current to move about, and therefore all the currents end up being 0, including this current for the short circuit current. So based on that, if I am tasked to develop a Thevenin model for this one, or Norton model for this one, V Thevenin or I Norton for both of those would be 0, which would leave us only, there's nothing wrong with that question, as long as we realize that since there is no independent source of energy here, the Thevenin voltage or the Norton current are 0. And basically that question is the same thing as calculating the equivalent resistance for this, because the second step for the Norton or Thevenin equivalency was to now calculate the R equivalent, and that R equivalent would be your R Thevenin and your R Norton. They're the same thing. So how did we calculate R equivalents? Well, the general approach to calculate equivalent resistors is to connect it to a terminal, is to put a test voltage here. We call it V test. Look at the current I test that is coming out of that source, and R equivalent is simply V test divided by I test. That's the definition of a resistance. Now, how do you do this now? Simple. You go back to labeling the circuit. I'm explaining this as if you don't know any other shortcut for it. So then you start labeling everything here. So that's your VT coming from the equation for this. You're going to call that V1. You can call that I1, I2, I3, I4. Now you write a KCL for this node. IT is equal to I1 plus I2. Write a KCL for that node. I2 is equal to I3 plus I4. Write equation for 1, 2, 3, 4 components. And solve that set of equations. And out of that set of equations, you're looking for VT over IT, as opposed to a specific value for VT and IT. You're looking for the ratio, and you can calculate that. There's an alternative way that sometimes it's easier for some people to give VT or IT in a specific value. So, for example, you can, if you're confused by the fact that you're not looking for a specific value for VT and IT and rather looking for a ratio, you can give this a hypothetical value of 1 volt, and at that point, once you calculate IT, if I put 1 here, and once you calculate IT, whatever that IT is, the inverse of IT would be your R equivalent, right? So that's another way of doing it. But now, going back to a bit of a shortcut and our understanding of what the network of resistors, how you can calculate the equivalency for network of resistors, we know that these two resistors are equal to each other, and the result is in series with that, and then the result of the whole thing is in parallel with 20, and that would be your R equivalent quickly. So that would be 20 ohm in parallel with 10 ohm that is in series with a 5 ohm that is in parallel with 40 ohm, and that takes care of that network. And so the equivalent of that circuit, the Thevenin equivalent, Norton equivalent, both of them is basically just one resistor. There is no V Thevenin, there is no I Norton. Now that we're clear about that, let's look at this alternative circuit, which is pretty much the same thing, with the only difference that this time we have a dependent source connected within that network. Now, this is going to make a difference in a sense that the simple calculation for R equivalency is not going to work. Before we get there, if I leave this network open, since still there is no independent source of energy within this circuit, leaving this circuit open, not connecting it, in other words, to any, not connecting it to any source of energy, means that all the currents and voltages in this circuit are going to stay as 0. So leaving this open means that V Thevenin is 0. Shorting it out means that it would result in I Norton being 0. So what's again left, like what we saw before, is that the equivalent resistance is the only portion of the Thevenin or Norton model that could be calculated for this circuit. The other part is 0. Now, again, how do we do equivalent resistors? Exactly the same thing. This time you can't actually use that shortcut. Because of this source being here, none of what we used here is true anymore. But we can always go back and use the basics, right? In other words, use the definition for resistance. We can connect this box to the test, look at I test, and divide the two by each other. And again, using the definition for resistor, V Thevenin divided by I Thevenin is your equivalent resistance, which is your Thevenin resistance, which is your Norton resistance. Okay, so how do we do this? Same way. Identify the nodes, and take that as our 0. This immediately becomes our V Thevenin because of the equation for that component. I'm going to call that V1. And there's another node here, if you notice. End of each component is a node, right? But that node has a known voltage equal to this. In other words, I can write this equation for that source, even though that is a dependent source. And that equation says this voltage minus that voltage is equal to 10Ix. This voltage being 0 means that that voltage is actually 10Ix. With that, I move on to labeling the currents. That's I1. This is I2. This current, I'm going to assume it's I3. Same current passing through I3, KCL for that node. And finally, that's Ix. We don't change that because that is given by the problem, and this equation depends on that current. Once I'm done doing that, I can move on to writing my KCL equation for components. So KCL, there's a KCL here, there's a KCL there. IT is going to this node, and I1 and I2 are leaving that node. For this one, I2 is going into that node, and I3 and Ix are leaving that node. Then we write the equations for components. So equations for components. We have a total of 1, 2, 3, 4, 5, 6 component. I already wrote the equation for this component to conclude that that's Vt. I wrote the equation for this component to conclude that that node is 10Ix. So we're only left with 4 components to write equations for. I1 is equal to Vt minus 0 divided by 20. For that component, I2 is equal to Vt minus V1 divided by 10. For this component, I3 is equal to V1 minus 10 Ix divided by 5. And finally, for 40x, Ix is equal to V1 minus 0 divided by 40. So let's count the number of unknowns. You can count Vt and It for now as your unknowns also, even though that's not true. So we'll discuss it. Vt, It, that's 2, 3, 4, 5, 6, 7 unknowns, right? Now, how many equations do I have? 1, 2, 3, 4, 5, 6. It appears that I have 7 unknowns by 6 equations. But keep in mind that I actually don't want to calculate the values for Vt and It. I want to calculate the value for Vt divided by It. And therefore, you can't count Vt and It as unknowns. You can actually assume that one is known and the other, in other words, these are parameters. Now, the other thing that you could do, like I explained, you can say that that's 1 volt, and then you can calculate It, the inverse of that. And once you do that, this becomes 1, that becomes 1. And now with that, you have 6 equations, 6 unknowns. You can calculate all of them, including It, and 1 over It is your equivalent resistance, and that shouldn't be too hard to do. With that, I'm going to conclude this lecture and also conclude the discussion on Thevenin and Norton equivalency. And from the next lecture, we're going to move on to the next chapter of the book when we start discussing other new electrical components that we haven't discussed before, and those would include capacitors and inductors. Thank you.